Welcome to the Rich Report, a podcast with news and information on high-performance computing. Today my guests are from VMware. We have Matt Herreras and Josh Simons. Welcome to the show, guys.
Great, thank you very much.
Well, thanks for coming on. Josh, you know, you've been a guest on many of my videos before, but let's do this podcast straight up here. I've brought your slides up. Why don't we go through the presentation and then follow that with a Q&A?
Sounds great.
So, Rich, I'm going to kick it off here. It's Matt Herreras, and I work in VMware's customer-facing systems engineering organization.
And this is Josh Simons. I work in the office of the CTO with a focus on high-performance computing and a background in HPC.
So the goal of our topic today is to discuss how we can increase agility and decrease time to solution for scientists and engineers using virtualization and cloud technologies. So in working with customers, we really see two fundamental areas, some problem statements that we found that we'd like to address. One of those is a fundamental tension between end users and administrators. We see that end users need compute environments that are customized and optimized for their specific requirements, while at the same time administrators need to deploy secure, cost-effective standard compute infrastructure. The problem is that this leads to disconnected islands of compute with security risk and cost inefficiencies. Now, another area that we see as a challenge is that current HPC job scheduling approaches are not agile. So we see job queuing delays, and that can increase time to solution. And we also may see an overcommitment of physical resources on cluster nodes. These lead to reduced cluster throughput and inherent inefficiencies in delivering scientific compute. How can cloud and virtualization help with these problems? Well, you can use virtualized HPC cloud infrastructure to simultaneously support the needs of both scientists or engineers and administrators, and you can leverage inherent virtual platform capabilities to increase cluster throughput and increase efficiency. Now, these will be the two main topics or solution areas for our talk today. But if you advance one more time, I'd like to point out that there's some other key value propositions to challenges that customers are facing that we don't have time to go into today, but may be worth a future discussion at another time. So we see that a virtualized and cloud computing approach can enable end-user self-provisioning of new compute resources, which is a classic use case for public infrastructure service providers. We also see that you can provide policy-based enforcement of fair share resource usage in multi-tenant environments. And you can automate secure, compliant, policy-based workload separation. And finally, we've seen that you can add fault recovery and avoidance capabilities to protect applications from hardware failure and to increase cluster throughput. As I mentioned, we're not going to go into those today, but I'd like to turn things over to Josh to maybe go into some detail about how we can address those first two bullet points.
Yeah, thanks, Matt. So let's get a little bit more concrete. Let's imagine that we have a sort of traditional HPC bare metal cluster. It's running some kind of a standard distro across all the nodes, and you've got a couple of application types that need to be launched onto the system. Well, as we all know, if those applications are not coded and compiled and tested to run in the particular environments that have been instantiated on this cluster, which we know is generally a homogeneous cluster, then you're out of luck, right? You've got to go off and find your own additional resources to go run these applications, and that leads to the islands of compute problem that Matt mentioned earlier. Now, of course, you could instead decide that you're going to, say, divide your cluster up into maybe a set of Windows nodes or a set of some kind of a Linux distro. The problem with that, of course, is that you've done the static distribution of your nodes, and it almost certainly is going to lead to a lower use or underutilization of your resources. So if we do the slide build and move into a virtualized realm, the scenario is a bit different. Right now, we have the hardware, and now we're running a virtualization layer across that hardware. And the individual researchers are now able to go and take their applications, wrap them in this virtual machine abstraction, along with the operating system that they need and any middleware that they need, the MPI libraries, particular math libraries, et cetera, and then they're able to schedule those directly onto this virtualized infrastructure. And if one group is using Windows and another is using Linux, it doesn't matter. They just pile them onto the virtualized infrastructure, and everything is sort of dynamically adapted to what the particular requirements are for that mix of user populations that you're dealing with. And if you think about life sciences as an example, there are a lot of sub-communities within the life sciences realm where they have, as a community, decided that they have very particular software stacks that they've standardized on. So if you want to allow those kinds of communities to jointly come together onto a shared resource, this approach allows you to do that while maintaining high throughput and efficiencies on the cluster. So if we go to the next slide, now once you've moved into this realm where you're now using this virtual machine abstraction and a hypervisor or virtualization layer for your clustering approach, there are several other benefits that accrue to you. So immediately, the fact that you have this VM abstraction wrapped around these individual OS instances and the applications gives you some data separation capabilities that allow you to do secure multi-tenancy. So if you have multiple teams that you're bringing together, and let's say you have HIPAA compliance issues in the life sciences space, or you're dealing with some kind of confidentiality of information, and you don't want to have jobs sharing access to that information, the VM abstraction gives you that separation that's required to maintain that. In addition, because you're running in these separate containers, you also now have fault isolation. So if application A fails, or it fills up /temp in one of the VMs that's running, say, OSA, it has no effect on what's going on with application B. So you eliminate the kind of cross-contamination that can occur in bare metal environments where you have multiple jobs running within a single Linux instance. And the last point there is something that seems somewhat counterintuitive, but we, in a number of instances, have seen cases where we can actually deliver better performance running in a virtualized environment than you would see running in a bare metal environment. And that's a longer conversation about why that happens, but we have a good sense of the driver of that particular phenomenon. So if we go to the next slide, we talked about kind of some of the attributes of a virtual machine. But there's another kind of cool capability in the virtual platform itself that we can take advantage of in interesting ways for HPC environments, and that's called virtual machine live migration. It's an ability to take a virtual machine that's running on one physical box in your cluster and move it from one box to another while the application is still running. It's a pretty fancy thing, but very much used in the enterprise, and as I said, something that we can use in interesting ways in HPC environments. And let me illustrate that on the next slide. So again, starting with the bare metal environment, what we're looking at here is a situation that's not uncommon in a batch scheduling environment where you have application C and you'd like to place it, but there's really no node. You don't have enough resources in one place to actually place this application. So you have limited choices in a bare metal environment that is doing static placement of jobs. You could either kill application A or kill application B and then schedule application C, or you could wait until either A or B finish and then schedule application C. Both of those lead to a lower overall throughput in your HPC cluster. So if we move into the virtual environment by doing the slide build, what you see here is that we can use that migration capability to move application A off of the left-hand node and then immediately schedule application C. So the idea here being that we avoid killing or pausing the jobs, and again, we increase overall throughput. If we go to the next slide. Yes.
Josh, if you don't mind, it's Matt, I wanted
Sure.
to jump in and kind of point out here that really brings together the concept that we mentioned as one of those first problems, which is that you have end users who need a customized experience, and then you need administrators who have a requirement to provide an efficient, available infrastructure. And this approach for bringing in the virtualization layer really unifies those two worlds, right? Because static job placement on top of physical infrastructure may be something you can do some intelligent placement at the beginning, but as things evolve, as environments change, for example, in the case of this new workload coming in, that's how you can basically make permanent the ability for end users to keep getting a customized experience while still providing those administrators that best use of the underlying infrastructure.
Yeah,
I want to make that point.
Well, hey, Josh, a point of clarification. I mean, is that a live application doing work that you're able to move while it's busy, or do you have to stop it and do a checkpoint or something like that?
Yeah, no, it's a live application, and the way it actually works is you can think about it as sort of demand paging. You basically move the pages of the running application over onto the new system, and you do this in rounds. So you let the application continue to run, and as it dirties pages, you continue to move those pages over until you get to the point where you have a small number of pages that it's continuing to dirty. At that point, you stun the first virtual machine, you move over the remaining small number of pages, and then you kick it off and it keeps running. So in actuality, there's a small delay, but it's a very small delay because you've moved the vast majority of the memory pages over while it's running.
Yeah, I seem to remember Sun touting this kind of capability with the E10K, right, with containers and things, but it looks like you've brought that into production and made it useful.
Yeah, it's a little bit, the way it's done is a little bit different, but in essence, it's kind of a similar approach, for sure. Yeah. Okay, so if we go to the next slide, let me give you one more example of where this live migration capability actually can be quite useful in HPC environments. And this particular use case is something that our EDA customers, the folks that are doing chip design, are actually quite keen to use because of particular issues that occur in EDA environments. But what we have here on the left side is a bare metal environment where we have a couple of jobs running. And if we do the build, what you'll see is a third job starts to run, and it starts using more memory than is available in the system. And we know what happens at that point. Everything gets really bad. We start swapping, and the applications begin running more slowly, which, again, this is a theme of what we're talking about. This, again, reduces the overall throughput of the system because these applications are going to take longer to complete given that they're swapping. So if we do the next build, you see what happens in the virtual environment is that, again, the third job starts running, but as it hits the resource limit on that first node, it automatically is migrated to the second node where there's room for it to continue to grow without interfering with the other applications. And that automatic migration is handled by capabilities that are built into the virtualization platform itself. There's a distributed resource manager there that's doing the sort of policy-based management and looking out for overuse issues in terms of resources and making these kind of decisions to automatically load balance workload across more nodes in the cluster. So if we go to the next slide, let's pop up a level here and talk a little bit about what an overall solution looks like. So the players here are you've got several research groups, and you have an IT organization. And the idea here basically is because this is a cloud infrastructure, is that the research teams are able to go in and automatically self-provision virtual clusters, these research clusters, and they can provision them as a set of virtual machines. The number of virtual machines and the size of the virtual machines, the number of vCPUs or virtual CPUs in each of these machines can be set to match the particular requirements of that research team. So you might have some that need small single CPU VMs and others that need SMP VMs because they're running, say, OpenMP applications. But that can all be customized. And the customization is done using this blueprint concept, which is a set of predefined templates, essentially, for different virtual machine types that can be instantiated in this private cloud, or private or public cloud, really. The nice thing about these blueprints, and one of the real benefits of this approach, is that the research team can have input into the content of that blueprint in the sense that they definitely have an opinion about which operating system or distro they want to run, which MPI library, essentially, what middleware they need, what software stack they want to run, what they need in that VM. By the same token, the IT administrator may be quite concerned about things like corporate security and data compliance issues. Those can be baked into the blueprints as well, so that both sides of the house essentially are satisfied when these research clusters are spun up. And then because you have multiple research teams spinning up these clusters on shared resources, you're assured that you're getting good usage of the underlying physical infrastructure while satisfying the disparate requirements of the different research teams and the IT organization.
Josh, it's Matt, if I can jump in again, I wanted to maybe point out here that, the title of our talk mentions hybrid cloud, and here in this slide we talk about both private and public cloud. And, many of the customer conversations that we have, the decision, isn't necessarily between, I have to choose either a private cloud or a public cloud to deploy my HPC workloads, but rather a much more comprehensive approach, a hybrid approach to cloud computing, which says I'm going to instantiate my HPC workloads on a private cloud infrastructure when the need suits me, but then I may want to be able to burst out to a public cloud provider. And another capability that we're talking about here is the ability to take those workloads and move them to a public cloud provider. And for those public cloud providers that are partners of ours, you can actually take, as Josh was describing, this fully vetted and built out cloud environment on the private cloud side that's been tested and configured for security and compliance and performance needs, and take that exact same logical infrastructure and port that to a public cloud provider. And the reason why that's important is we talk about getting a faster time to solution, getting scientific agility. You don't have to rebuild your environment from scratch in a public cloud. You can take the blueprint for it, and you can take it to the public cloud already built and established. It also reduces risk, of course, because anytime you have to put too many hands on something and rebuild something from scratch, the chances that you might misconfigure something, the chances of that go up. So this approach really can help customers get up to speed much more quickly and eliminate the risk if they leverage this approach of doing a sort of a like-for-like cloud, logical cloud architecture. So if we can go to the next slide, maybe I can kind of summarize what we've been talking about here. What we're really talking about is a new approach to delivering HPC resources using cloud and virtualization technologies. And this approach can uniquely address the conflicting needs of end users and administrators, kind of unifying them together in common cause, if you will. And also, we talked about how we can move away from a traditional static job placement to a much more flexible, dynamic environment that can raise throughput and increase scientific agility, which is really the end goal here. How can we do, better science faster? And of course, if we can do it at a lower cost and make sure that things are compliant and secure, that benefits everyone.
Absolutely. And if I could chime in a little here. So we've spent most of our time talking about kind of the business value and a little bit on some how some of this works under the hood. But I did want to take a couple of minutes just to talk about kind of what's going on at a more technical level. So VMware is quite interested in the HPC space in terms of it being a pretty significant workload that we would like to virtualize. We are continuing to drive improvements into the platform to address and to continue to expand the range of HPC workloads that can be addressed with virtualization. Just as examples of that, the latest release of our virtualization platform kind of elevated the idea of latency-sensitive workloads to a first-class entity in the platform, where it's now possible to say, when you create a virtual machine, that this virtual machine is destined to run latency-sensitive applications. And that's important, as many of you know, because latency sensitivity is a hallmark of many HPC applications. It's either storage latency, interconnect latency, it could be memory latency. There are lots of different places where this shows up. So treating that as a first-class entity and automatically setting tunables within the platform, which is an evolving story for us. We'll set initial tunables now and then more tunables over time, is an important part of what we've been pursuing, both within the office of the CTO and also within the R&D organization generally. We're also doing a pretty significant amount of work around RDMA, looking at InfiniBand and Rocky, and looking at that obviously for low latency and for CPU offload, and doing not just RDMA but also virtualized RDMA. Again, so we've just sort of touched the surface here of all this. We have on the next couple of slides some papers and a pointer to our blog that I would really recommend. If we go to the next slide, in particular, I would recommend taking a look at the CTO blog site, which I've been using to share a lot of information about our HPC efforts. There are some other technical papers listed here that may be of interest. I call your attention to the latency white paper listed at the bottom, which is actually quite critical for getting good performance on the platform. This is a set of guidelines for tuning our platform for the most part. It's not about application tuning. It's about virtualized platform tuning to get good performance. That's an important one. If we go to the next slide, we've got papers on big data and Hadoop, InfiniBand performance, and some of the work we're doing around para-virtualized RDMA. So it's a range of topics which we hope you will find interesting and useful. If we go to the next slide, we're essentially done with the content that we would like to present, and both Matt and I really invite anyone that's listening who's interested in learning more about our HPC work, having a discussion about this. Please get in touch with us directly. We'd be more than happy to speak with you in more detail. And Rich, if you have questions, we'd be happy to answer those too.
Well, great. Josh, I liked how you guys started this out with Matt talking about the user, right? Because we had this virtualization panel at SC13, and the fellow from Cambridge, I remember he saying, you have these scientists walk up and say, I need to be root to run my thing. And they're like, no way, Jose, right? That just doesn't happen. I'm curious, did the origins of virtualization, was that happening, that kind of thing in the enterprise that gave rise to this?
Yeah, so I think it wasn't one of the drivers, but certainly the fact that, so dev test was one of the early areas where VMware was playing, and certainly the ability to get root access is useful in some of those situations. And as you said, the fact that we can give root access while not, allowing the user to destroy the world is a pretty cool capability, because they're locked up inside their virtual machine, and it's all nice and safe. And if they do something bad, we can just blow it away and give them another VM again later. So yeah, it's something that is certainly used, on occasion in the enterprise. And we think it's a nice fit in the HPC space as well, especially when we're talking about, when you're talking to multiple constituencies at an organization that is thinking about consolidating and centralizing multiple islands onto islands of compute onto a centralized resource. They are resistant to that, and they, in a bare metal world, have legitimate reasons for that. And one of them tends to be, hey, I'm going to give up control. I can't have my root access, right? So again, we can give them that root access. We can give them the ability to bring their own software stack onto the shared resource. So yeah, it is a useful capability.
Okay, so I was curious. You brought up this resource broker, Josh. Now, is that a facility within the VMware stack, or could I bring in something like the stuff we know about, which is Univa Grid Engine or Moab or something like that?
Yeah, that's a really good question. There are a couple of different ways you can think about mixing virtualization into an HPC environment. And in the method that we're describing here, where you create these virtualized HPC clusters, we didn't say this explicitly, but in those scenarios, you would continue to run Grid Engine or LSF or whatever DRM you're normally using within those virtual sets of virtual machines. Now, the nice thing about that is that the end user, the end scientist, continues to interact with the job scheduler in the way that they have before. So their world doesn't really change. What does change is the ability to, to move those virtual machines around and bin pack them efficiently and do some of the things that we've talked about earlier in the presentation. The other way of doing it is to continue to use the standard batch scheduler as your main mechanism for interacting with the cluster. And then, as you know, these systems, for example, Grid Engine, have been extended so that they understand how to instantiate or spin up VMs for themselves. And in that case, you're getting less of the benefit that we're offering, because the self-provisioning and some of the other capabilities that we wrap around all this, and live migration, et cetera, become more difficult to take advantage of in that environment. But this built-in distributed resource scheduler that we have, which is that policy layer at the hypervisor level, is something that could be used in either of those situations.
And Josh, I'm curious. I don't want to put you on the spot here, but I've been told that VMware has proliferated because it works really well on the Intel software stack. But as you know, in HPC, there's all kinds of architectures and AMD and all kinds of other things. Is this going to be hardware dependent going forward, or what do you see?
Yeah, so that I have to be a little careful how I answer that. But what I would say is that certainly x86 is the dominant ISA in the enterprise. And to be frank, the enterprise is a vastly larger market than the HPC market, and so the enterprise is what's going to primarily drive the directions that we go in. Now, happily, there's a huge amount of convergence going on between the requirements in the sort of traditional HPC space and in the new and emerging requirements in the enterprise space. So a lot of what we do in the enterprise now has increasing relevance for HPC. But at the end of the day, our direction will primarily be driven by the enterprise. And x86 is still the dominant factor. And I guess what I would say is, though, if other ISAs emerge as important players in that space, then I think you could assume that VMware would be interested in that.
Yeah, yeah. And I guess while we're talking about markets, is HPC is this interesting from just a technology perspective, or do you guys see a business case that VMware could make some hay here?
Yeah, sure, I do, but I'm going to let Matt answer that one.
Yeah, sure. We really do. And you can see here from this joint presentation, I'm in the field organization working directly with customers, and Josh is in the CTO's office. That's, I think, a very, almost clear answer to your question, which is, VMware sees the collaboration between what our engineering organization is building from a technological, capabilities perspective, and what the solutions are for our customers. That, the things that we described earlier in this presentation are needs that have not been cooked up in a lab by VMware, but rather what our customers are asking us to do. And those customers include EDA, as Josh mentioned, financial services, life sciences, and we have several engagements we're working on right now with customers who have reached out to us proactively saying, we have these problems, can you help us solve them? And anytime a customer comes to you, that implies there's a market there. And so we absolutely are interested in pursuing this and are actively doing it.
Well, terrific. That this panel I mentioned, guys, I know you've seen it, Josh, the video of that, but it was entitled, virtualization. Are we ever gonna? Is it ever gonna happen for real? And the panelists were all using various forms of virtualization to do real HPC work. And I asked them, will we need a panel like this in 5 years? Or will virtualization be more common? And they said, no. In 2 years, it's going to be everywhere. It's going to be all over the show floor. Would you guys agree with that? Or is this more of a longer-term play?
No, I thought that was a great panel. I really enjoyed watching it, maybe partly because that's what we've been preaching for a while now. But yeah, I think certainly for the throughput-oriented applications, so the sort of non-MPI applications, there's really no reason to not use it's a double negative there. There's every reason to use virtualization and cloud-based approach for those kinds of applications. The knocking down some of the barriers for the more difficult or more stringent requirements that you see for some of the really latency-sensitive MPI applications is going to take a bit longer. But that's going to happen. And again, kind of harking back to what I said a minute ago about the enterprise, we're seeing a lot of increased requirements for low latency in the enterprise, which really gets us interested and excited about addressing that problem. Of course, it helps the HPC space tremendously as well. But again, as sort of the big brother, the sort of the elephant in the room, enterprise being so much bigger, it will drive significant interest on our part. So yeah, I think over the next several years, it will be it will become part of just another tool, essentially, that is commonly deployed within HPC.
Well, Matt and Josh, this has been fascinating, and it's really fun to watch these two worlds converge, and especially when it's something that's going to help the users with flexibility and everything you guys can bring to the table. So I want to thank you both for coming on the show today.
Great. Thanks, Rich.
Yeah, thank you.
You bet. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on high-performance computing.